Thanks everybody for joining. This session, I am going to cover introduction to indexes in SQL Server. This is a beginner level session, and the things that we are going to cover in this session could honestly, every single one of these chapters could be a session on their own. However, I'm just going to cover, the surface level, the intro layer of some of the important concepts you should know if you're not sure how to go in and index your SQL Server. Before we dive into that, let's just introduce myself a little bit. My name is Goran. I have been a BI developer for 9 years. 7 of those 9, I have been a BI team manager. The last 4 years I've spent as an Azure DBA and a DevOps engineer. And in my free time, I am an open source contributor here and there. The latest open source project I've contributed to is Eric Darling's Performance Monitor, which if you're a small team and you haven't used a performance or you haven't tried this performance monitor, I highly advise you give it a shot. It's pretty good. The link is there. You can get it off of GitHub. Pretty easy to install. Personally, I am a bit of a foodie. Yes, that is an entire cake. I am on a Peruvian kick currently. Awesome food, highly recommend it. I love dogs. I think they're awesome. I'm a terrible guitar player, and I ride motorcycles on the both sunny days we get in Ontario. Enough about me. Let's talk about today's agenda. So this session is going to be divided into 3 logical parts. In part 1, we're going to be talking about data structures. In part 2, we're going to be talking about basic rules of indexing. And in part 3, we're going to be talking about certain optimization things, index recommendations, tipping point, consolidation. Before we dive into that, let's just briefly cover why indexes are even important, right? So indexes, they dramatically reduce your disk I/O, right? Searching an index is much faster than scanning an entire table. Indexes have fewer columns per row, and data is in some sort of a sort order. They improve your query performance because of that. The query optimizer evaluates available indexes, picks the most efficient retrieval method, and it avoids costly full table scans, right? Therefore, this all consumes fewer system resources. Your well-designed indexes are going to help your selects, updates, deletes. Obviously, they're going to consume less CPU. There's going to be less memory pressure. And they can, of course, help with your deadlocks and blocking, right? So this is one of the things that is a bit of out of scope for this session because, like I said, any one of these topics can be a session on its own. But just know that well-indexed database, it's not going to have a lot of issues with deadlocks and blocking. There's also a downside to having too many indexes. If you have way too many indexes, you're going to have slower data modification because every insert, update, and delete must also update all affected indexes. It adds overhead. You have increased storage costs because each index consumes additional disk space. Wide indexes with many columns kind of amplify this point. You're going to get a higher memory footprint, right? Because more indexes means more pages competing for the buffer pool. You have concurrency problems. Excessive indexes can increase lock contention during modifications. You have a maintenance burden because your maintenance windows are now going to be longer because you have to maintain all of those indexes. You're going to eventually hit the point of diminishing returns because the query optimizer is not going to use every index you have, right? So creating many speculative, let's give the optimizer choices is actually not a good, it's a design mistake, if you will. So the key takeaway from this quick overview is that, this is sort of a cobbled together quote from Microsoft Learn, right? Index design, it really is a balancing act. You really want to have a few well-targeted indexes as opposed to just kind of create as many as you can. So with that said, let's dive into part 1. So in part 1, we're going to cover certain data structures. I want to focus on cluster indexes and non-cluster indexes, but we will mention heaps as well. There are other data structures in Microsoft SQL Server for sure, but those are out of scope of this session. And again, before I dive into part one, let's do a quick commercial break sponsored by Microsoft Learn. I need to explain a couple of things so that the next section is actually going to make sense. One of those things are logical reads. So what even is a logical read? So logical read occurs every time the database engine requests a page from the buffer pool. Like if the page isn't currently in the buffer cache, a physical read first copies the page from the disk space into the cache, and then the page is read. Right? So in short, one logical read is one 8K page accessed from memory. It's kind of like the unit of measure SQL Server uses to measure how much data the query touched, regardless of whether the data came from the disk or it was already cached. You can observe this cost if you use set statistics IO on before you run your query. And the logical reads output in the field that you see is going to, this is going to mean the number of pages you read from the cache, and then the physical section, like the physical reads, is kind of the subset of that number. The second bit that I need you to be aware of is the query execution plan. You can think of it, you can think of the query execution plan like, let's say when you ask a SQL Server a question, right? Like when you run a query, a SQL Server doesn't just blindly go find the answer, right? It needs to go figure out the best way to find that answer. And that planning process is handled by the component called Query Optimizer. And the resulting recipe that the Query Optimizer comes up with is this execution plan, right? It is particularly important to note the cost associated with each node of the plan and to identify how indexes are used or not used in the various nodes, right? So query execution plan helps you see that. You have three flavors. You have estimated. You can run that before you run your query to kind of see what the estimated execution plan looks like. Actual execution plan runs, you can see that after your query is completed, and live query statistics, like you can watch that happen as your query is running. You can watch those live. And then concludes our commercial break. So let's dive back into the data structures. Okay. So a heap is a table without a cluster index, right? So data is stored without any sort order, and SQL Server uses the page free space to track the available space and generally appends new rows to the last allocated page or a new 8K page, right? There is no sort order governing where that data lands. As you can see in this little example, that person ID is all over the place, full name all over the place, preferred name, so on and so forth. And you can think of these 8K pages kind of like sheets of paper, as I've tried to illustrate here. These sheets of paper are what hold all of your data. All of your rows and all of your columns live on these little sheets of paper, these little 8K pages. Now, because this data is not stored in any logical order, if you want to retrieve any piece of information, like if you want to look for a Brian, there's no way for you, or SQL Server in this case, there's no way for SQL Server to know where Brians are or how many Brians there are in this data set. So when I run a query that searches for a Brian, I need to look through every single one of these records on every single page in order to retrieve that information, right? I don't know where they are. I don't know how many of them are. And if you want to look at that query in SSMS, right, you remember I set statistics IO on. This is going to help us see how many logical reads this query produced. And if I execute this query and then I look at the execution plan, I see that I have a table scan here indeed. So I scan the entire table and I have produced 99 logical reads. So I have touched 99 pages in order to return one record where I have a person with preferred name, Brian. That sounds a bit expensive, right? On the other side of the coin, we have cluster indexes. A key characteristics of a cluster index are that the data is actually logically sorted by the index key. Right? The cluster index is effectively your table. The heap no longer exists, and now the cluster index takes over the role of the table. Therefore, obviously, you can only have one per table. Leaf level of a cluster index is where all of your rows and all of your columns are going to live. So every bit of data that you have in this table, that's where it's going to live. And there is a second piece of the index, which is a B3 or a B+3, which is used for the navigation. Right? It gives you an ability to do an index seek as opposed to scanning the entire table. The syntax for creating a cluster index is create a cluster index, you give it a name on your table. In my case, that's application.people, and then I am using person ID as my index key. You can have one or multiple columns in your index key, but in my case, I just want to use person ID because I want to sort the data on person ID. You can also have a cluster index be your primary key in the table as well. The syntax is slightly different. Alter table, table name, add constraint, you give it a name, primary key clustered, and then you select your the column or columns you want to use in your key. You run it, and then you create your cluster index / primary key. Oh, so now if we go back to our little sheets of paper, our 8K pages, and we have, after we have created this cluster index on person ID, we can see that now our data is actually sorted by person ID 1, 2, 3 through 3,261 apparently in this data set. Great. So this is now going to help us if we want to search for people based on a person ID, right? I don't need to scan the entire data set. I can just dive bomb exactly where a specific person ID sits. The cluster index under the hood looks like this. So remember I mentioned a leaf level. This is that leaf level. That's the 8K pages that contain all of our data, and above it or on top of it, however you want to think about this, is the B+3, which helps our navigation, right? And that B+3 holds the information on where every person ID is, because that's the key that we use to build our index. So if I want to search for a person with person ID 1001, my query optimizer knows exactly where to go and which path to follow in order to return the data where person ID equals 1001. And if I look at the query that I've just executed, select full name from application.people where person ID equals 1001, and I have my set statistics IO on, and I look at the query execution plan, I see that indeed now I have an index seek as opposed to a table scan. And if I look at my logical reads, I see that the SQL Server only needed to append or use 2 logical reads in order to get that data. 2 much more efficient than 99, right? Perfect. However, if that obviously works if my where clause has a condition that says give me a person ID equals something, obviously, because the data is sorted on person ID, right? But if I want to execute something like this, right? If I want to go back and I want to find my Brian from my first example, because Brian's a great cook, makes great pizza, and I really want to get in touch with him, so I need that information. If I execute this query and I look at the query execution plan, I can see that I'm back to scanning the entire index. That's again, I only know how the data is sorted based on the person ID. I have no idea where Brian's are, how many Brian's are there. So I need to scan the entire thing again. Like, that's not very helpful. A quick break in our regular programming just to explain 2 more things which are going to be relevant for the next chapter. And the next chapter is going to help us find Brian's. So stay with me here, please. I need to explain what key columns are in an index. So the columns the index uses to search and sort the data are called key columns, right? So you've seen in that the syntax that I've used to create a clustered index, I've used person ID. So that person ID, where it's set, is actually my index key now. And as you've seen, when I've used person ID as the index key, the data became then sorted by that key, right? It sorts by the person ID. It works exactly like order by, if you can imagine that, right? So if you say sort data by person ID and then last name, you're going to get data sorted by person ID first and then last name second. Usually in key columns, you want to use columns that sit in your where clause, in your joins, in order by. And an example that I've had here was, imagine that you want to search for customers by postal codes, right? So you would use postal code in the key. But if you also wanted to see additional information about those customers, like an address, right? You could add that address as an include because you don't need that data to be sorted by address. You just want to find people fast by postal code, and then you want to see their addresses. Now, the include columns are effectively your extra columns stored alongside the index. They are not used for searching or filtering, right? They're just something that you have in your select. Yeah, like I said, they are the columns that are not used, that you're not using for filtering, but it's just additional information that you wanted to see that you don't necessarily want to go back and fetch from the cluster index, just to kind of make your query cheaper. And this is your rule of thumb, right? If you're filtering sorted by a key column, if you just need it in the results, include column. Okay, that's that. Let's talk about non-clustered indexes now. So non-clustered indexes are separate structure alongside a table, alongside our cluster index. They contain the columns that you choose. So cluster index contains all of the columns. Non-cluster index is going to contain the columns that you choose, plus the cluster index key, which is auto-added. You don't need to add it automatically. If you are building a non-cluster index alongside a heap, then you obviously don't have a cluster index key. You have a row ID or a pointer to a row. And the sort order is independent of the cluster index, obviously, because you're going to be sorting on something else, on a different column that you choose. If you don't have a column included in your non-cluster index, but your select is asking for it, you are going to create a key lookup, meaning that you are going to go fetch that data from your cluster index, and you will see what that looks like in the upcoming slides. One rule of thumb is that you actually want to avoid volatile columns. You don't want to use columns that update frequently and add them to your non-cluster index because that just adds overhead. And you want to avoid very large columns like varchar max, XML columns, JSON, although SQL Server 2025 does support indexes for JSON. So watch this space. Okay, back to non-cluster indexes and what they look like. So remember, we tried to search for a Brian. We don't know where it is. We've spent a whole bunch of logical reads to find Brian. So, that was too expensive, took too long. So we decided to build a non-clustered index, and we are going to use preferred name as our index key. So we're going to build a non-clustered index on preferred name, and what is going to happen automatically. Remember, clustered index key is going to be automatically included. So my non-clustered index is actually going to look something like this: preferred name, and then the person ID is going to come along for the ride. The syntax for creating a non-clustered index is create non-clustered index. You give it a name on your table, and then your key. In my case, that's going to be preferred name. So now let's see what this looks like. If I want to say select person ID preferred name from application.people where preferred name equals Brian, if I run this now, and I look at the execution plan, I see that I only ever have an index seek on my non-clustered index that I've just built. There's nothing else. There's no sort. Obviously, it's just one record. Person ID and preferred name live in this index. So it's the only data structure that I needed to touch to retrieve this information. But if I expand this query a little bit, if I say, give me person ID, preferred name, full name, and email address. So full name and email address don't exist in my non-clustered index on preferred name. And then I execute that query and I look at the execution plan. I see that I still have my index seek here on preferred name. That's exactly what I would expect. but I also have this key lookup. And this key lookup means that I've used that key, I've used that person ID key to go back to the cluster index and grab the full name and email address for this record so that I can bring it back in my select. And if I look at the logical reads for this query, I can see that I have spent a bit more logical reads in this case. So I don't need 2 logical reads anymore. I actually needed 4 logical reads, but that's perfectly fine. Non-clustered index and what it looks like under the hood is something like this, right? So you have your leaf level with all of the data, you have your B+3 for navigation up there, and the leaf level contains, like we said, it contains data that you have included in the non-clustered index, plus the row locators. And the row locators are either a cluster index key in case of a cluster index or a pointer to a row in case of when you actually don't have a cluster index, but you have a heap instead. Quick tip, usually heaps obviously have their place, but usually you probably want to create a cluster index more often than not. And this is the end of our part 1. In part 1, we covered heaps, tables without any order. Every search is a full table scan, unless you have additional non-cluster indexes to accompany that heap. Cluster index is now your table with sorted data. It has that B3 for navigation, and then non-cluster index is those are indexes with user selected data columns plus cluster index key or row locators in the case of heaps. Excellent. If you do have any questions about this, please hold until the end, and I will be glad to help. Hey, part 2, let's talk about basic indexing rules. So in part 2, we're going to talk about basic indexing rules when it comes to the where clause, where you have equality and inequality at the same time. You have just seen me work with the query where there's just one equality. It's pretty straightforward. Here, we're going to talk about equality, inequality. We're going to talk about order by and how you index for those. And then we're going to talk about how do you actually index for joins. Now, before we continue, I have to say, this is an intro level session. There is a lot that can be discussed here. We're not going to do a deep dive into index. We're not going to master indexing here, right? We're just going to cover a couple of basic rules that can put you in a good spot. If you follow these rules, you're going to be correct or fine more often than not. But obviously, there's going to be, cases where somebody asks you, what's a perfect index for this case, and you're going to end up saying, well, it depends, right? Because it's true. And it's kind of funny when I was reviewing this session with my awesome mentor, Andy Yoon, we kind of ended up having this conversation where like, yes, this what you're saying makes sense, but if you look at this, we were just actually discussing the in and what happens with an in when you have one value versus an in with multiple values. It ended up being this discussion. Yes, but if you have this scenario with an in, and if you look at the way it's actually executed, and all of that, it was a good discussion. But that was kind of going down the path of now you're talking about really, really super fine tuning indexes and mastering every single little aspect. And that is a bit out of scope of this session. Here, we're going to cover basic rules, but I definitely encourage you to go and explore more because it's a vast topic and you can do a lot. The more you know, the better your system is going to be. Okay, so let's start with the basic rules. Before we talk about equality and inequality, let's define what those two are for SQL Server. Equal is equality, in behaves as equality, in with a single value is essentially flat out equality, in with multiple values is like a bunch of separate equalities. Is null is equality, inequality, obviously the non-equal signs is not null, like and not like, right? So what do you do when you have a where clause that looks something like this, right? So from my application.people, I say where preferred name equals David and logon name does not equal no logon. In this case, since you're filtering on both of these columns, you want to take these columns and put them in the key of an index. But how do you pick which column is first, right? Basic rule of thumb is you want to lead with equality first, and then you want to tack on inequality. Of course, there will be cases where this depends, right? But for a basic level, if you follow this rule, you're going to be in a good spot. Your goal is essentially to reach the smallest result set the fastest and then filter from there, right? And usually equality is going to get you there faster than inequality. Usually, not always. Let's talk about indexing for order by. So if I have a query that says select logon name last edited by from application.people where last edited by equals 1, order by logon name. If you remember from my from my previous slides, we created a clustered index on person ID, so I can search on person ID, no problem, and a non-clustered index on preferred name. I can search on preferred name, no problem. I cannot search on last edited by, and because of that, if I look at the execution plan, I end up having a cluster index scan because I have to, read everything to find last edited by equals 1. I have a sort here because of the order by, so I am actually making my very expensive SQL Server vCores do the sorting for me. Not great. And the SQL Server is giving me an index recommendation. It's like, hey, buddy, you should probably go ahead and create this index because it looks like you really need it. And it's not wrong, except that it is wrong. Let's see why. Let's take this recommendation, this exact recommendation that the SQL Server is offering, and let's build it. So we're going to say create non-clustered index recommendation on application.people, last edited by in my key, and then include logon name. If I execute this query now after I built the index, I see the index seek, but I still see the sort, right? So, it did help me, the seek, but I'm still asking my SQL Server cores to sort the data for me. And there's no need for that. What you really should be doing is you should create a non-clustered index. You give it a name on application.people, last edited by, comma, logon name. You want both of those to be in the key of your index so that the data comes pre-sorted. And when the data is pre-sorted, and then you execute the query, you see that you're using that index, you're seeking, and there's no sort anymore. Now, this can be tricky at first to kind of figure out what this looks like and what this data, how is it going to be sorted? Is this actually going to work? There's a little bit of a trick to that. You can actually visualize your index. So let's say that I want to see what this index looks like. Would that actually make sense for what I'm trying to do if I want to avoid a sort? You can write a simple select where you're going to just list the columns that you have in your index key, and then you want to put those columns in the index key, you want to put them in the order by in exactly the same order. So now when you execute this query, you can actually see how the data is sorted. And you can see that, it actually, for the query that I was running, this actually makes sense because it comes pre-sorted. Couple of basic rules for indexing for order by. If you have equality and order by, you want to append the sort column at the end of the key. So you lead with equality, you append order by at the end. If you have equality, inequality, and order by, usually you would want to lead with equality, you want to follow by order by, and then you want to tack on inequality. If you have top and order by and inequality, it depends. It depends on how this statement is actually true for any one of these rules. In general, if you follow these rules, you're going to be fine. But of course, there's always that it depends, right? And all of it depends on how selective your queries are. And what that means is, if you have an inequality that says where person ID is less than 1, right? And you have no person ID is less than 1. that is a very selective query because that's not going to return any results. And if that's the case, it doesn't make sense to lead with the order by. Just lead with inequality first and then tack on the order by. But if the query that you're asking for is not very selective, you say where person ID is greater than 0, so basically return every single person ID, then in those cases, you want to lead with order by, and then you want to tack on that inequality column at the end. It's a very silly example, obviously, but you know what I mean. If you're not very selective, the query is returning many records, leave with order by first. Okay, let's talk about indexing for joins. Let's say that I have a query where I have a join between two tables. My select is asking for columns from both of the tables. Obviously I have an inner join here. I have a where clause from one of the tables, and I have an order by from the second table, right? So there's a lot going on. So if I execute this query and I look at the query execution plan, I see a whole bunch of things. I see a cluster index scan. There's an index seek on a foreign key. There's a key lookup. There is an index recommendation. There is a sort. There's a whole bunch of things happening, right? It kind of looks scary, right? What you should do is take that query, take the two tables and spread them apart, right? Separate them out. Take all of the fields from the one table, put them on one side. So I have my application.people on the left, my where clause, where preferred name equals Kayla, because preferred name comes from application .people table. And on the right-hand side, I have everything that comes from purchase orders. I didn't have a condition in my original query. There was no where condition on purchase orders table, but I did have a join. And you want to treat your join as a filter because that's essentially what it is, right? So treat the join as a filter and build a where clause based on that join. So I have here where contact person ID equals 2, and that's my ID for Kayla. So now when you look at this, you suddenly realize, holy guacamole, I actually know how to index for both of these cases. I know that when I have equality, I just create a non-cluster index on that equality. And when I have equality in order by, I create a non-cluster index where I lead with equality and I tack on the order by at the end. And then I have a couple of small columns in my select, which are not filtering any data. I don't need them sorted, so I can just dump them into the include part of the query. So my two indexes would look like this, right? Create a cluster index, application of people, preferred name in the key, and then on the other side, you have creating an index on purchasing, purchase orders, contact person ID, leads, order date is the second in the index key. And then you have your include supplier reference is order finalized because you're not filtering on those. You don't care about the order of those columns. So now you build those indexes, you run the query, you look at the execution plan, and you get two index seeks on the two non-cluster indexes. Perfect. Now, I will admit, I still have the sort here. And I was just kind of bashing that sort and how you should not be using SQL Server. SQL Server is expensive course to sort the data and all that. And, yes, I am guilty, I admit it. But however, I have reduced my logical reads, and remember those logical reads are reading those sheets of paper, right? I have reduced them from 14,000 to 34. That is a huge, huge performance improvement, right? Imagine if you needed to read 14,000 pages versus 34 pages. Perfect. So indexing for joins, just remember to break the join into single table queries and then index those independently. You'll be good. Treat the join column as a filter. And remember, the joins do benefit from pre-sorted data. Even if you don't have a where condition on the tables that you've joined, you still want to index for that join. And that's the end of our part 2. Right? So in part 2, we covered the where clause with equalities, inequalities. We covered order by with append where we said you just append the sort column to the key. If there is equality, then we talked about certain cases with equality and inequality and all that. And then we talked about joins where we decomposed the queries into single table queries. The biggest takeaway from this is it depends, right? No, but all joking aside, this is a solid starting point. This is not the end all and be all. We could literally have a 1 hour session about each of these to kind of get into the nitty gritty. But overall, if you follow these rules, you will be okay. Not perfect, but you will be okay. Welcome to part 3. So in part 3, we're going to talk about index optimization. Couple of well, I'm not sure why I call this index optimization. It's not really index optimization. Just the last part is index optimization. The first 2 bits are, we're going to talk about SQL Server index recommendations, why you should not listen to those. We're going to talk about the tipping point and why your SQL Server is not using the index that you built. And then we're going to talk about consolidation of indexes. If you're old enough, you're going to remember Clippy. Clippy was this, I guess, AI in Microsoft Word, which was super eager to help every time you tried to type in even half a word. And it was like, oh, it looks like you're writing a letter. And you were just trying to type out a shopping list or something. It's trying to be helpful. It wasn't really helpful. Brentozar refers to SQL Server index recommendations as Clippy. And I thought that was hilarious. And apparently Brent thinks it's hilarious as well. So I'm going to be calling this feature Clippy mainly because it's funny, let's be honest, but also because SQL Server index recommendations is just a bit of a mouthful. So Clippy, you remember in our previous slides, it was very eager to tell us, hey, you should really build this index because it is pretty awesome and it's going to help you so much. And then we proved that honestly, it wasn't that great. Like we could go in, it was helpful. Don't get me wrong, right? It was much better than not having an index at all. But it wasn't perfect. Like we could easily make it better than what Clippy was saying we should be doing. So when you see these recommendations, just don't take them at face value, copy pasting and building whatever Clippy says. Don't do that, but do take it as a sign that there is work to be done. Clippy's recommendations, they come from these system tables, from system views, from like these DNVs, where the data is accumulated over time, and it just kind of uses those data points, to give you suggestions. It suggests super wide indexes, which probably shouldn't have. It doesn't deduplicate. And what I mean by this, I should have corrected this slide, to be honest with you, but what I mean by this is Clippy does not care what indexes you already have. It doesn't care that you are running a query. You have an index on preferred name, but you're running a query that also includes an email and logon name. It doesn't care that you have an index on preferred name that could be expanded to include those 2 columns that you're now looking for. It is flat out going to suggest, hey, build an index on preferred name, but also include these columns, right? So it doesn't consolidate, it doesn't deduplicate these indexes. It doesn't get thrown for all queries. It doesn't recommend filter indexes, column store indexes, which honestly we also didn't cover because it's a little bit out of scope of this session. And it doesn't specify correct order of columns. It is, to be fair, pretty good when it comes to equality and inequality. Like it will suggest a correct index for that scenario. But if you have a where clause with 3 equalities, it's not going to suggest those columns in a particularly useful order. It's just going to list them as a comma delimited list of whatever order they're in your table. So when you have something like that, you see a recommendation, you kind of have to figure out which one of those 3 is the most selective one and then go from there. Because remember, you want to narrow your search space as fast as possible before you do anything else. Cool. So Clippy, thank you for your service, but calm down a little bit. Don't trust it. Just take it as a sign that something needs to be done, and then try to figure out what's the best thing that you can do for that particular section. Okay, let's talk about a tipping point. This is a pretty cool subject. I actually kind of enjoy this, and honestly, we could again have a session on the tipping point alone with all the demos and everything. But I am going to try to explain it in short form. So stay with me here. Let's say that we have this query where we say select preferred name, email address from application.people where preferred name equals Kayla. And the only indexes that I have are my clustered index on person ID and my non-clustered index on preferred name. So my non-clustered index on preferred name does not have email address. So I'm going to go, if I run this query, I'm going to have to go back to the clustered index to grab the email address so that I can deliver these results. Right? So if I run this query and I'll look at the execution plan, I see this is exactly what's happening. I get an index seek on my non-clustered index on preferred name, and then I get my key lookup on back to my cluster index to get that email. This is exactly what you would expect to see. I'm using the index that I've built. Perfect. Awesome. Here's a kicker, though. Oh, it's not a kicker. Actually, here's a data point that I need you to be aware of. I have about 1,300 people in this people table, and those 1,300 people are stored on 104 8K pages. So 104 8K pages is an important piece of information. If I go back to my people table and I update 30 random records, I update their preferred name from whatever their preferred name was to Kayla. So now I have 30 records where preferred name equals Kayla, and I have 104 pages where all of this data is stored. And I execute my query now, right? Preferred name, email address, where preferred name equals Kayla. If I execute this query now, I no longer get my index seek and the key lookup. Instead, I get a clustered index scan. So the query optimizer figured out it's actually cheaper for me to scan the entire clustered index as opposed to go and seek for 30 Kaylas and then do additional key lookups to bring those email addresses back. And that's the tipping point. So the tipping point happens when a non-clustered index seek plus a key lookup becomes costlier or almost costlier than a clustered index scan. It is driven by rows to pages ratio, and this is why I told you to remember those 104 pages versus my 30 records. So 30 in 104 is just under 30%. It typically occurs when estimated rows exceeds 33% of the number of pages in the table, but this is not a hard and fast rule. Obviously, as you've seen in my example, I had just under 30% of rows compared to the pages, but I still managed to get the tipping point. And this is, sometimes it's going to be less than 33%, sometimes it's going to be more than 33%, but in most cases, it's going to happen around 33%. And it's affected by joins, by, whatever your queries are doing. So the 33 is not hard and fast, but that's commonly when it does happen. And this is why your index is not getting used, right? So when you see a tipping point happen, if you can help it, there are a few questions you can ask yourselves to see if you can avoid it, right? You can ask, can your queries return fewer rows? Maybe they can, maybe they cannot. Is pagination an option? I don't know. Can your users run more selective searches? Maybe they can, maybe they can't. Can my query live with fewer columns? Maybe you really do need all of the columns. Who knows? Maybe you don't. If you don't, then cut the columns that you don't need. How large are the columns that you really need? If they're small columns, add them to the non-clustered index. If they're large columns, I would just leave those in my clustered index and just do the key lookups. how frequently are the columns updated? If they're not volatile, like there's no changes to them, add them to the non-clustered index. If there's something that updates frequently, just leave them in the base table. It's not worth the overhead cost. And I love this quote from Brent Ozar. Like really, like all of these questions like this, they don't have a correct answer. Right? They're just kind of like little guides that can help you get to the best performance possible. That is a tipping point. So let's talk about consolidating indexes and what even is that. So now you've been sitting through this session for about 50 or so minutes. I'm not entirely sure. And you're like, wow, this is the best session I've ever seen. This is amazing. So you're so excited and you're taking this link and you're sharing it with your colleagues and you're like, guys, you got to see this. This is awesome. And now everybody's watching this session. Everybody's like, this is insane. We now know how to index. And everybody goes crazy. Like, you're creating indexes. Bob over there is creating indexes. Sarah over there. Sarah has actually seen this session the day before. She just didn't tell anybody because she got so excited and she started creating all these indexes. It was just, body time. So everybody's creating indexes, their own indexes. Nobody's actually double checking which indexes even exist in the tables that they are indexing. So you end up with a situation where, Bob has created an index on preferred name. You have created an index on preferred name, but you've also included logon name. Sarah over there has an index on preferred name, is employee, include email address, and everybody's happy because all of your queries are working great. However, now you have all these copies of an index that are essentially borderline identical, right? If they lead with the same column, or if they have the same leading key, these are great candidates to merge. So what you can do is you take these three indexes, just merge them into the one index where you say index preferred name, comma, is employee in your key. And then you have your include section with the email address and logon. Two crucial pieces of information that you need to remember is that key column order matters. So you need to preserve that. Include column order does not matter because those are columns that you're not filtering on. You don't care about the sort order of those. You just want them along for the ride so that you can avoid the key lookups and you can avoid the tipping point and all those good things. And also, by the way, if you have this index now, finding a Brian from the beginning of this session would be a breeze. And you can get that tasty pizza that he knows how to make. And this is the end of our part 3. So in part 3, we talked about Clippy. It's a hint, not a solution. Don't trust it. We talked about the tipping point. Very interesting. There's a bunch of resources out there. I encourage you to go out and read about them. Kimberly Tripp, Greg Gonzalez, Brent Ozar, they all have great resources on these things. And then we talked about consolidation, right? You want to merge your overlapping indexes because you don't want to pay for that storage. You don't want your maintenance to take 2 days and what have you. So, just keep at it, keep creating the indexes, but also make sure you clean up your environment. And that's that. That is my entire session. Hopefully, you all found it useful. You've learned something. Remember, the main rule, it depends. So, this is not the end all and be all of all of the indexing rules. This is kind of like your first stepping stone in the right direction. But there's a lot more to dive in and figure out. If you want to contact me, feel free to send me an email. This is my contact information, my email, my LinkedIn, and you can download this slide deck from my GitHub. And these are your resources. I encourage you to give them a try. And that is all I have. If we have time for questions, I'll be happy to answer them. Otherwise, thank you, everybody.